Video on Determination of Special Loads from IS Codes. In this video, you will learn about the wind loads on buildings, factors affecting these loads, and determining the parameters from the IS codes to calculate these loads. Wind refers to the movement of air relative to the surface of the earth. Wind, being a fluid, is composed of circular eddies of varying sizes and rotational characteristics. These eddies give a gusty or turbulent character to the wind, which causes significant effects on the objects that come in its way. So what if this wind encounters a building in its path? The building surfaces resist the flow of the fluids over them. The fluids exert a reaction force on the buildings, which is called drag. It's vortex shedding in the building, in the opposite direction of the wind flow, which creates a tremendous load on the building, as displayed. Let us try to understand them in detail. The drag coefficient is used to quantify the drag or resistance of an object in a fluid environment, and it differs with the shape of the body that the fluid encounters. In general, drag coefficient is not an absolute value for a given body shape, but it varies with the speed of fluid flow, or more generally with the Reynolds number of the fluid. The image shown illustrates the drag coefficient for different body shapes, for a fluid of Reynolds number approximately 10 to the power 4. The Reynolds number for wind, having turbulent flow characteristics, will approximately be around this value. As you can notice, for the same fluid velocity, the drag or the resistance is much higher in the non-streamlined body shapes like cubes and cylinders. Thus, while designing tall structures, engineers take into consideration the shape of the building, and prefer shapes having lesser drag coefficient. This is to make sure the wind flows past the building smoothly, and does not cause friction, due to higher resistance. Vortex shedding refers to the unsteady oscillating flow that takes place when a fluid flows past a non-streamlined body at certain velocities, depending on the size and shape of the body. The vortices produce a force that acts on the body in the crosswind direction. Thus the fluid flow past the object creates alternating low-pressure vortices on the downstream or backside of the object, and the object will tend to move towards the low-pressure zone. This phenomenon, when applicable in buildings, causes swaying of the building in the horizontal direction, which might lead to failure of the structural members, due to excessive deformation. The vortex shedding, along with the corresponding crosswind movement, for bodies of different geometries, are displayed. Here too, the building shape affects the amount of vortex shedding on it. The building with openings in it has the least crosswind movement, and hence the vortex shedding is also quite negligible. The crosswind movement, and hence the vortex shedding, is more prominent in the other shapes, as seen. This is why engineers are constantly coming up with innovative building shapes and designs, which can reduce these effects of wind on the building. These are some of the modifications done in building shapes to enhance their performance against wind forces, by reducing the vortex shedding and drag. You must have noticed these unique shapes in some of the famous high-rise buildings in the world. Let's take a look at a few examples of buildings that have incorporated these shapes. Sometimes, the corners are modified to be stair-stepped. The Taipei 101 Tower in Taiwan has this design. The stepped corners, which make the corners rough, and thus reduce the vortex shedding effects, as the eddies created become smaller. The proposed 102 Incheon Tower in South Korea has through openings in them. These slots will allow reduction in wind forces, as some of the wind will pass through, and thus, the resulting sway due to vortex shedding will also be reduced. Engineers have also designed buildings that have a rotating and twisting shape along the height. The Kine Tower in Dubai is designed in this way. The rotating shape minimizes wind load on a building surface, preventing wind direction, as the wind does not attack on the entire surface of the building throughout its height. The twisted shape helps to avoid simultaneous vortex shedding along the height of the building, as the wind will hit from only one particular direction at one time. Now that you understand the effects of wind load on tall buildings, let us look at the magnitude of the loads and how they are calculated. In analysis and design of tall buildings, the wind load to be calculated depends on some parameters, which are based on the locality the building is constructed. The Indian Standard Code 875 Part 3 states the considerations for calculations of wind load in India. Design wind speed is the artificial speed for which the structure is designed. It is calculated with the consideration that the structure so designed can withstand the actual wind loads. According to the IS 875 Part 3, the design wind speed Vz is given by Vb times K1, multiplied by K2, multiplied by K3. Where Vb is the basic wind speed of a particular area, K1 is the probability factor or risk coefficient. K2 is the terrain, height, and structure size factor. And K3 is the topography factor. You have to refer to the IS code to determine each of these parameters in order to find the design wind speed. This map from the IS code represents the basic wind speed Vb in different regions in India. Thus, depending on which place the building is to be constructed, you can find out the Vb. This table in the IS code lists the K1 factor, which depends on the prevailing wind speed and the design life of the building. In this course, a mean probable design life of 50 years is considered, and accordingly, the K1 factor taken is 1. Next, the terrain category refers to the surroundings of the building to be designed. Based on the heights of the nearby buildings, you will be considering the terrain category, which are categories 1, 2, 3, and 4. The structure classes of 3 types, Class A, B, and C, depending on the greatest horizontal or vertical dimension of the building. If the dimension is less than 20 meters, the structure class is A. If it is between 20 to 50 meters, the structure class is B, and it is C for dimensions more than 50 meters. Once you know the structure class and terrain category, you can refer to the Table 2 in the IS code, which mentions the K2 factor for buildings of different heights. After determining Vb, K1, K2, you are left with determining the last parameter, that is K3. The topography factor, K3, depends on the upwind slope at a particular place, and is more effective if the slope is more than 3 degrees. The upwind slope is the slope of the wind in the windward direction. If the upwind slope in a place is less than 3 degrees, K3 is taken as 1. The K3 value varies from 1 to 1.36 if the upwind slope is more than 3 degrees. Now that you have the Vb, K1, K2 and K3 values, you can determine the design wind speed Vz by putting the values in the formula mentioned before. After calculating the Vz, you will find the design wind pressure, Pz, by using the formula, Pz equals 0.6 Vz square. This Pz, in kilonewton per meter square, is the load value applied on the building external claddings. After applying the wind loads, you can run the wind analysis on the building, and determine the responses, such as story displacements, and internal forces and stresses. You will learn to find these parameters more clearly, as you proceed with the upcoming DO videos. In the next video, you will learn to define the wind load in the ETABS software. Thanks for watching.